Alrighty, for our last essay questions, I'm going to explain Dalton's law, Henry's law, and explain how these laws are used to explain oxygen and carbon dioxide. And so Dalton's law basically says that the total pressure is going to be equal to the sum of all the partial pressures. And so how how it relates to O2 and carbon dioxide. It's essential for carbon dioxide and oxygen because if we can understand the partial pressure of one, then we should know the partial pressure of the other. If we are given the partial pressures of every other gas, except for oxygen, then we can deduce based off subtracting partial pressures of carbon dioxide and whatever other gases we may have, and then we can be left with oxygen. And this could be helpful because if someone's not getting enough oxygen, we can find out, we can get what should be, or instead of having, we can judge our actual based on our theoretical. And so if our theoretical was like 70, or not 70, well, let's just throw a number out there. If our theoretical was 20 and the person was only getting 15, which these are terrible numbers, but then we would know that, okay, something's up, our numbers aren't adding up right, one is a lot lower, something's going on with this person. Henry's law says how, was that Dalton's law? Sorry, that was Dalton's law. Henry's law says how that the gas that's dissolved into a liquid or anything is directly proportional to the pressure of the liquid. This basically means that if we take the pressure and we multiply it by the solubility coefficient, we can actually get the concentration that will be in there. So if we have a partial pressure of like 50 and we have a solubility coefficient of 1.21, then we can get a concentration of, I don't know what this is going to be off the top of my head, like 61-ish or so of a certain gas. Just higher partial pressures is going to lead to more concentration. If we have the same gas in two different containers, but one has a lot more partial pressure than the other, then we know that this one is going to be concentrated a lot higher because they're the same gas, so they'll have the same solubility coefficient. So, yeah. That is Henry's law and Dalton's law. Let's see what the next question is. Explain the alveolar gas equation and how the information it gives us might be used. So the alveolar gas equation is going to be PaO2 is equal to FiO2 multiplied by the pressure of the atmosphere minus pressure of H2O minus PaCO2 over R. And R is going to be the respiratory exchange ratio. Normally, for a normal person, it's going to be about 0.85, but it can range from 0.7 to 1, depending on if you're metabolizing a lot of fats or if you're metabolizing a lot of sugars. And so this is used to just calculate the partial pressure of oxygen in the alveoli. So this is going to be pressure in alveoli of oxygen. And so what we use is how much oxygen is going to be inspired when we inhale. And so this is always going to, I shouldn't say always, but almost always 0.21%. Now, pressure in the atmosphere is going to change depending on where you are, but sea level it's going to be 760. And then we're going to minus it by partial pressure in water vapor, which is around 50. And then whatever the partial pressure of CO2 is in the human being. And so this can basically help us figure out if there's an adequate exchange of oxygen happening. We can find out either problems if the person's hyperventilating or if they're just not diffusing correctly. That's what this is for. What does it say? Finally explain ventilation and perfusion ratios and give examples of what might cause these ratios to change. So this is going to be called VQ ratio. And this is quite simple, V over Q. Basically, what this is V is going to be the amount of air reaching the alveoli, so volume of air reaching alveoli. I'll draw right here. So it's how much air is getting into the alveoli. And then Q is going to be the amount of blood that reaches the alveoli. So if we have a catheter here, that's going to be the blood that reaches here as well. There's going to be blood. And so a high VQ can be caused by, if we know fractions well, by lowering the denominator or increasing the numerator. And so we can either get a higher VQ ratio by breathing in a lot more, but really what we can get from a high, or the easiest way, I should say, more common way of having a high VQ ratio is going to be caused by having an embolism. So if we have, a lot of a blockage here, we're going to have a lot less blood that can make its way in. And so that is going to lower our Q drastically. And so if we have something that's like, let's just throw some numbers out there, 10 over 10, it's going to equal to 1. But if our Q changes to 2, then this actually changes to 5. So drastic change, 500% increase. Low VQ is the opposite if we either increase Q or decrease V. One of which is going to be a lot more common, which is going to be just more like airway obstruction. So if we have problems with our breathing, if these get obstructed, or if in our lungs themselves we have mucus, and so the fluid, or the amount of air that we can intake is going to be a lot lower because we have space being taken up by this fluid that we have in our lungs now. That's going to decrease our volume. So that's going to in turn give us a lower VQ ratio. Alrighty. Let's see what next question we have. Explain total pulmonary and alveolar ventilation rates and describe why slow, deep breaths are more beneficial than rapid, shallow breathing. So pulmonary ventilation, which is also referred to as just like our minute ventilation, is just going to be tidal volume times our breaths, which we're given an F, or I guess our respiratory rate. So how many breaths we take a minute would be, I guess, a better way to say it. Respiratory rate. So if our tidal volume, let's say, is like 800 milliliters, and we're breathing 20 times a minute, then we're taking in, did I do that math right? Yes, we're taking in 16,000 milliliters every minute. And that would be our minute ventilation. Minute ventilation, or also known as pulmonary ventilation. So alveolar ventilation is going to be sort of similar, but it's going to be the amount of air that's reaching the alveoli per minute, but it excludes the dead space. And so alveolar ventilation is tidal volume minus dead space times our respiratory rate as well. And so if we had tidal volume 800 milliliters, but our dead space, because Here's our alveoli. Right here, no gas exchange happens here. This is just dead space. So if this is like 200 milliliters, then that's 200 milliliters of air that we are breathing in, but we're not using for gas exchange. So that's actually going to be 600 milliliters times our respiratory rate of 20 breaths a minute, which is going to give us 12,000 milliliters a minute. So this is 16 liters, and this is going to be 12 liters, which is a noticeable difference, because this is how much air we're able to breathe in, take in from the atmosphere. But this is how much we actually have going on in our gas exchange. So the benefits of slow, deep breaths is because it's going to increase alveolar ventilation. It's going to make that a lot more effective, alveolar ventilation, allowing for better gas exchange. If we're just breathing in and breathing out really quick, we're not actually allowing the gas exchange to happen. We're also not filling up this much of our alveoli. Remember, we still have dead space we have to get through first before we can get through the rest of it, which was 600. So if we're just taking a lot of rapid, deep breaths, rapid, shallow breaths, we're not filling this up as much as we can. And this could in turn go from 600 to, let's just say, like 400. Oh, that's 4,000. 400, which then means 400 minus 200, we're going to be left with 200 milliliters times our 20 a minute, which in turn gives us only 4,000, which is only 4 liters a minute, which is, did I do my math right over here? Yeah, I did. 800 was our tidal volume. 600 was the alveoli. Yes, okay. Sorry, math is hard. But, so that's what happens if we take rapid shallow. But if we can increase this instead, and let's say we go from 20 to like 15, but we increase this to not 600, but let's say we increase this to like 900 milliliters. All right, let's just go to 800. Wasn't it 800? No, 800. Then we're going to have 800. Wait. I did do my math wrong. Sorry. Regardless, the premise is the same. I was trying to go off this equation with tidal volume, or total tidal volume, dead space, and alveolar ventilation. I apologize. But the premise is the same. If we have shallow but rapid breaths, we're not getting enough into the actual alveoli themselves. But if we take slower but deeper breaths, we're going to have a lot more that overcomes that tidal volume and makes its way into the alveoli, increasing the amount that can be used for gas exchange. Sorry. Alrighty. And the last questions we have: describe COPD and restrictive lung disease. Between these two diseases, mention what emphysema would be, and then explain the mechanisms of air trapping in emphysema. Alrighty. Use mechanisms of air trapping in emphysema. Okay, so COPD is going to be chronic obstructive pulmonary disease. And it's just a group of diseases that include emphysema. And basically, it just means you have obstructive an air disorder. So there's two different kinds, as we know. There's going to be obstructive and restrictive. Obstructive basically means that you can breathe in. It's not as hard for you to breathe in as compared to a normal person. That may be a little different, but it's not too different. But breathing out is going to be an issue. Emphysema is a type of disease that also involves the alveoli walls are going to be sort of destroyed. And so a normal person will be like this with millions of these things lined up. And so they have all of this space. I didn't draw this one right. Or, well, they have all this space for the alveoli, but with emphysema, it sort of destroys this, and we end up getting these branches of alveoli that are a lot bigger. And so breathing in is not going to be too hard, but breathing out is going to be an issue for them because there's going to be a lot more that they're going to need to press down on to actually get the air out of the alveoli. Air trapping and emphysema. So air trapping and emphysema occurs due to loss of elasticity and a collapse of the airways during exhalation. This is going to also sort of hyperinflate the lungs, which is going to then increase residual volume. And let me just look at the last question and explain the mechanisms of air trapping and emphysema. Yeah, I'm pretty sure between these two diseases mention what emphysema would be. Oh, and then the mechanisms of. So obstructive disorder is going to be, you can't really breathe out that well. Restrictive lung disease is going to be you can't really breathe in that well. It's going to be pretty hard for you to breathe. Emphysema is going to be obstructive. And then air trapping is just a collapse of the airways during exhalation. And so it's not going to be as elastic as a normal person's lung would be. And yeah, that is it for question 4.